Dear learners, welcome to the course Electromagnetic Fields. In this video, we will discuss about the various coordinate systems in electromagnetic fields. To describe a vector accurately and to express a vector in terms of its components, it is necessary to have some reference directions. Such reference directions are represented in terms of various coordinate systems. There are various coordinate systems available in mathematics, out of which 3 coordinate systems are used in this course. A point or a vector can be represented in any coordinate system which may be orthogonal or non-orthogonal. There are 3 important coordinate systems: Cartesian coordinate system, cylindrical coordinate system, spherical coordinate system. We will discuss these coordinate systems one by one. Let's start with the Cartesian coordinate system. It is also called as rectangular coordinate system. This system has 3 coordinate axes: x, y, z. These x, y and z axes are mutually perpendicular to each other. These 3 axes are intersect at points. This is the point of intersection. The axes intersected at common point called origin of the systems. There are 2 types of systems called right-handed system and left-handed system. You note down the difference between right-handed system and left-handed system. The right-handed system means if x-axis is rotated towards y-axis through a smaller angle, then this rotation causes the upward movement of right-handed screw in the z-axis direction. So this is right-handed system. Here x is moving towards y. Here you note down in the left-handed system, y is here and x is here. So compare with the right-handed system, the position of x and y is different. Here the rotation of x into y is like this. The right-handed system is very commonly used and followed in this course. In Cartesian coordinate system, x equal to 0 plane indicates 2-dimensional YZ plane. Y is equal to 0 plane means it indicates 2-dimensional XZ plane. And Z is equal to 0 plane indicates 2-dimensional XY plane. This figure illustrates representing a point in Cartesian coordinate system. A point in rectangular coordinate system is located by 3 coordinates, namely x, y and z coordinates. The point can be reached by moving from origin, the distance x in x direction, then distance y in y direction, and finally the distance z in z direction. In this illustration, this point P is x1, y1 and z1. That means x1 is the distance moving in the x direction, and y1 is the distance moving from the origin at a distance y1. Similarly, z1 is the distance from origin. Say for example, we consider this point q3, minus 1, 2. That means x is 3, y is minus 1, z is equal to 2. So we have to move a distance 3 from the origin, and y is in the negative axis, in the negative direction, is minus 1. It is moving in minus 1. Y is minus 1. Similarly, z is 2. So the intersection of these 3 planes gives a point P in rectangular coordinate system. This figure, it illustrates the intersection of x equal to 3 plane, y is equal to minus 1 plane, z is equal to 2 plane. So now we imagine that the intersection of these 3 planar surfaces gives the point P in rectangular coordinate system. This figure illustrates unit vectors in Cartesian coordinate system. As we know that generally unit vector is represented as A vector, small letter A vector, a letter A with overbar it, and X, it represents the subscript, it represents the direction of unit vector. So AX vector means unit vector along the X direction. Similarly, AY vector is the unit vector along Y direction, and AZ is the unit vector along Z direction. So Cartesian coordinate system, AX, AY vector, AZ vector are the unit vectors or base vectors. So in the previous video we discussed about unit vector. Unit vector is a vector whose magnitude always unity, and it indicates the direction of vector under the consideration of coordinate system. Here we consider the coordinate system as a rectangular coordinate system. What are the coordinate points? X, Y, Z. So therefore it is indicated as AX vector, AY vector, AZ vector. So therefore the base vectors or unit vectors are very important in representing a vector in terms of its component along the three coordinate axes. Before going to discuss about the differential elements in Cartesian coordinate system, let's have a small look about position and distance vector. Consider a point P. This is the point P is x1, y1, z1 in Cartesian coordinate system. Then the position vector of point P is represented by the distance of point P from origin, directed from origin to point P. This is also called radius vectors. Position vector is r vector OP, that is equal to x1 AX vector plus y1 AY vector plus z1 AZ vector. The magnitude of this vector in terms of three mutually perpendicular components is given by modulus of ROP vector is root of x1 square plus y1 square plus z1 square. Say for example, we consider the point P is 1, 2, 3 means the position vector can be written as 1 AX vector plus 2 AY vector plus 3 AZ vector. Now consider 2 points in a Cartesian coordinate system P and Q with the coordinates x1, y1, z1, x2, y2, z2. For this is point P and this is point Q. So we are going to find the distance vector between the point P and Q. We just take the difference of position vectors. We know how to write the position vector at point P. The components are, vector components are x1, y1, z1. So P vector can be written as x1 AX vector plus y1 AY vector plus z1 AZ vector. Similarly, position at point 2, at point Q, Q vector is x2 AX plus y2 AY vector plus z2 AZ vector. Now we are going to take the difference of P vector and Q vector. We will get the distance vector from P to Q. The distance vector is otherwise called as displacement vector. We are going to write the distance vector from P to Q, which is represented by PQ vector. PQ vector is equal to the difference of Q vector minus P vector. That is x2 minus x1 ax vector plus y2 minus y1 ay vector plus z2 minus z1 az vector. The magnitude of the vector is given by modulus of PQ vector is equal to root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. So now we are very clear about the position vector and distance vector. So using the basic concept of unit vector, we can find the unit vector along the direction of PQ. So we could represent A vector PQ is equal to unit vector along PQ, that is vector by modulus of vector, that is magnitude of vector. Here we consider a vector as PQ vector. So therefore unit vector is equal to PQ vector divided by the modulus of PQ vector. Next we move on to differential elements in Cartesian coordinate system. So this figure illustrates the differential elements in Cartesian coordinate system. Consider a point P x, y, z. This is point P. It is x, y, z. Let us increase each coordinate by a differential amount. A new point P dash will be obtained having coordinates. This is new point P dash having the coordinates x plus dx, y plus dy, z plus dz. That means this is point x, y, z. It increase at a distance dx. Dx is the differential length in x direction. Dy is the differential length in y direction. Dz is the differential length in z direction. So therefore the new point P dash is new point is x plus dx, y plus dy, z plus dz. Point P is x, y, z and P dash is x plus dx, y plus dy, z plus dz. These 6 planes together define a hence differential vector length, also called elementary vector length, can be represented as dl vector is equal to dx ax vector plus dy ay vector plus dz az vector. So from this we calculate the magnitude of differential length vector. Modulus of dl vector is equal to root of dx square plus dy square plus dz square. The differential volume of rectangular parallelepiped is given by So this is the vector joining original point P to new point P dash. dl vector is the vector joining original point P to new point P dash. Now point P is the intersection of 3 planes, while point P dash is the intersection of 3 new planes which are slightly displaced from our original 3 planes. These 6 planes together define a differential volume which is a rectangular parallelopiped as shown in this figure. The differential volume. The diagonal of this parallelopiped by a differential vector length. The diagonal of this parallelopiped is the differential vector length. Hence, the differential volume of the rectangular parallelopiped is given by dV is equal to the product of the differential length in three different directions. That is dx, dy, dz. Let us define differential surface areas. The differential surface element ds vector is ds an vector, where this an vector is a unit vector normal to the surface. This figure illustrates differential surfaces in Cartesian coordinate system. The differential surface normal to x direction is dy dz. This is normal to x direction, normal to x. So here an vector is ax vector. So in this case an vector is ay vector. The differential surface normal to ay vector is nothing but dx dz. So similarly the differential surface normal to az vector is dy dx. So the vector representation of these elements is given by ds x vector, ds y vector, ds z vector. These are the vector representation of these elements. Next we move on to cylindrical coordinate system. In the cylindrical coordinate system, the coordinates are r, phi, z. In the case of Cartesian coordinate system, coordinates are x, y, z. These three are planar surfaces. Therefore, the range of variables are from minus infinity to the plus infinity. But in this case, r is the radius of the cylinder. So, therefore, the range of variable is from 0 to infinity. And another variable is phi. Another coordinate is phi. Phi is from 0 to 2 pi and z is from minus infinity to plus infinity. In the cylindrical coordinate system, it consists of three surfaces. The point P in cylindrical coordinate system is nothing but the intersection of the cylinder with the radius r, and phi is equal to constant plane and z is equal to constant plane. The intersection of these three planes give a point P in cylindrical coordinate system. This is the point P which shows the intersection of the cylinder and azimuth plane, and z is equal to constant plane. So the intersection of r is equal to constant and phi is equal to constant is a straight line, and similarly the intersection of r is equal to constant and z is equal to constant is a circle. So we should remember here r, phi, z, where r is the radius of the cylinder. Unit vectors in cylindrical coordinate systems are ar vector, a phi vector, a z vector, where ar vector is the unit vector along the r direction and a phi vector is the unit vector along the phi direction, and a z vector is the unit vector along the z direction. So this is the unit vector along the z axis and this is the direction of phi. So it is a phi vector. Here this is the radius in the radial direction. Unit vector is a r vector. A r vector. So now we represent the p vector in cylindrical coordinate system as P vector is equal to PR AR vector plus P phi A phi vector plus PZ AZ vector. Where this PR, P phi and PZ are vector components in cylindrical coordinate system. Next, the differential elements in cylindrical coordinate system. So here we consider a point P. This is the point P R phi Z in cylindrical coordinate system. Let each coordinate is increased by the differential amount. The differential increments in R phi and Z are dr, d phi, dz respectively. Now there are two cylinders of radius r and r plus dr. There are two radial planes at the angles phi and phi plus d phi. And there are two horizontal planes at the heights of Z and Z plus dz. All these surfaces enclose a small volume. The differential lengths in R and Z directions are dr and dz respectively. In phi direction, d phi is the change in angle phi and it is not the differential length. So due to the change d phi, there exists a differential arc length in phi direction. This differential length due to d phi in phi direction is r d phi. So we should remember this, where d phi is the differential amount of angle. So here we are writing the differential length in phi direction. Hence the differential vector length in cylindrical coordinate system is dl vector is equal to dr AR vector plus r d phi A phi vector plus dz AZ vector. The magnitude of the differential length vector is given by modulus of dl vector is equal to root of dr squared plus r d phi the whole squared plus dz squared. Hence the differential volume of differential element formed by the product of the differential length in three different directions. That means dv is equal to r dr d phi dz. The differential surface areas in three directions are illustrated in this figure, where this dsr vector is the differential surface normal to r direction. Similarly, ds phi is the differential surface normal to phi direction. This is phi direction, normal to phi direction. This is dr dz. Similarly, the differential surface normal to z direction. Normal to z direction is a z vector dr or d phi. The vector representation of these differential surface areas are dsr vector is equal to r d phi dz ar vector. ds phi vector is the differential surface normal to phi direction. This is nothing but dr dz a phi vector. Similarly, ds z vector is differential vector surface normal to z direction or dr d phi az vector. Next, we are going to discuss about the relation between Cartesian and cylindrical coordinate systems. Consider a point P whose Cartesian coordinates are x, y, and z, while the cylindrical coordinates are r, phi and z, which is illustrated in the figure. It is marked as a red color circle. Looking at the xy plane, we can write x equal to r cos phi and y is equal to r sin phi. So from this we can write r is equal to root of x square plus y square. Tan phi is equal to y by x. This is the transformation from Cartesian to cylindrical can be obtained from the equation, that is r is equal to root of x square plus y square, phi is equal to tan inverse y by x and z is equal to z. So using these equations, note that r is positive or 0. Hence positive sign of square root must be considered. While calculating phi, make sure that the signs of x and y. While calculating phi, we should consider x and y, sign of x and y. That means whether it is positive or negative value. If both are positive, if both are positive, that means x and y. If both are positive, x and y are positive, it is lying in the, we consider both are positive, x and y are positive, it is lying in the first quadrant. This is x and this is y, so it is lying in first quadrant. So therefore the phi is positive. If x is negative and y is positive, then the point is in the second quadrant. This is the second quadrant. That means x is negative, y is positive, this case. And phi must be within plus 90 degree to, phi should be from x negative and y positive, means phi is lying from 90 degree to 90, phi is lying from 90 degree to 180 degree plus 180 degree. That is within minus 180 degree to minus 270 degree. Say for example we consider x equal to minus 2, y is equal to 1. we consider x equal to minus 2 and let us consider x equal to minus 2, y is equal to 1. Then phi is equal to, we calculate tan inverse y by x. That means tan inverse 1 by minus 2. The actual value is minus 26.56 degree. But it should be lying between minus 180 degree and minus 270 degree or plus 90 degree to 180 degree. So therefore we should add 180 degree. So hence when x is negative, it is necessary to add 180 degree to the calculated phi value. To add 180 degree to the calculated phi value, 154.43 degree. Next case, when y is negative and x is positive, then phi is in fourth quadrant, that is from 0 degree to minus 90 degree. It is nothing but from 270 degree to 360 degree. Similarly, when x is negative and y is also negative, the point is in third quadrant, and accordingly phi must be between 0 to 90 degree or minus 180 degree. That is, it should be lying between plus 180 degree to 270 degree. So 180 degree must be subtracted from phi calculated by tan inverse function to get accurate phi when both x and y are negative. It is in the fourth quadrant. We consider x equal to minus 3, y is equal to minus 3. So in this case, we have to subtract 180 degree. We obtain 45 degree. Next, we move on to spherical coordinate system. Spherical coordinate systems, here we consider three surfaces. One is a sphere with a radius r. Another one is a right circular cone with apex angle theta. The intersection of sphere and cone is the horizontal circle. The third surface is half plane, which is perpendicular to xy plane. Here the coordinates are r, theta, phi. So the range of variables for r, it is 0 to infinity. So here in the spherical coordinate system, r is the radius of the sphere, but in the previous case, r is the radius of the cylinder. Both are different, and phi is 0 to 2 pi, and this phi is the azimuth plane angle. This is same as that what we discussed in the cylindrical coordinate system, and theta is the apex angle, which is from 0 to pi. It is half angle. This figure illustrates the intersection of sphere, cone and half plane, which is nothing but a point P is in spherical coordinate system. And this figure illustrates the unit vectors in spherical coordinate systems. Unit vector along r direction is ar vector, along phi direction is a phi vector, along theta direction is a theta vector. So we know that how to represent the vector in spherical coordinate system. The vector of point P can be represented as PR AR vector plus P theta A theta vector plus P phi A phi vector. Similarly, here also we consider a point P, which is in a spherical coordinate system, r theta phi in a spherical coordinate system. consider a point P, r, theta, phi in a spherical coordinate system. That each coordinate is increased by the differential amount dr, d theta, d phi. The differential increments in r, theta and phi are dr, d theta and d phi. Now there are two spheres of radius r and r plus dr. There are two cones with half angles theta and theta plus d theta. There are two planes at the angles phi and phi plus d phi measured from xz plane. All these surfaces encloses a small volume which is shown in this figure. The differential length in r direction is dr. The differential length in phi direction is r sin theta d phi. The differential length in theta direction is r d theta. The differential length vector dl vector is equal to dr ar vector plus r d theta a theta vector plus r sin theta d phi a phi vector. The magnitude of differential length vector is modulus of dl vector is equal to root of dr the whole square plus r d theta square plus r sin theta d phi square. We know that differential volume is the product of the three differential length in three different directions. dv is equal to r square sin theta dr d theta d phi. Next we move on to the differential surfaces in three different directions. Differential surface normal to AR direction is nothing but the product of r d theta, r sin theta, d phi. That means r squared sin theta, d theta, d phi is the differential surface normal to r direction. The differential surface normal to theta direction is ds theta vector, r sin theta, dr, d phi. Similarly, differential surface normal to phi direction is ds phi vector is r dr d theta. Next we are going to discuss about the relation between Cartesian and spherical coordinate systems. You look about this figure. So from this we can write x equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta. So x equal to r sin theta cos phi, y is equal to r sin theta sin phi and z is equal to r cos theta. From this we can find r value. So x squared plus y squared plus z squared, substitute the expression and it is simplified as r is equal to root of x squared plus y squared plus z squared, while tan phi is equal to y by x. So that means phi is equal to tan inverse y by x. Cos theta is z by r. So therefore theta is equal to cos inverse z by r. This equation represents the relationship between Cartesian and spherical coordinate system. That means x, y, z values are given. From this we can calculate r, theta and phi. Say for example x equal to 1, y is equal to 2, z is equal to 3 means we substitute x, y, z value in these expressions. We will get r, theta and phi. I hope now we are very clear about three different coordinate systems such as rectangular, cylindrical and spherical coordinate systems, and also we discussed relationship between Cartesian and cylindrical coordinate system and Cartesian and spherical coordinate systems. Thank you.